Electrolysis is the decomposition of some substance by means of an electric current. In this lesson, we're going to be looking at electrolytic cells. Electrolytic cell is a cell that requires electrical energy to cause non-spontaneous redox reactions to occur. Up until now, we've been looking at electrochemical cells, or voltaic cells, and these cells spontaneously produce electricity from a chemical reaction. An electrolytic cell is the exact opposite. It utilizes an external source of electrical energy to force electrons to flow in the opposite direction by applying a voltage greater than the cell potential. In essence, it converts electrical energy into chemical energy. The best way to imagine an electrolytic cell is think of a rechargeable battery. As you're using the battery in your device, it's an electrochemical cell that produces a spontaneous reaction, and it uses a chemical reaction to produce electricity. Eventually, that battery will go dead. You'll place that battery into its recharger and then you'll plug it into the wall. Once it's plugged into the wall, it becomes an electrolytic cell, where it uses the external source of electricity to force a chemical reaction. This is a side-by-side view of an electrolytic cell versus a voltaic cell. A voltaic cell or galvanic cell is a spontaneous reaction that releases energy. Electrons are freed at the anode and they flow towards the cathode. In this case, the anode would be Fe and the cathode would be Cu or copper. For an electrolytic cell, which is a non-spontaneous reaction that absorbs energy, notice the change. The Fe is now the cathode and the Cu or copper is now the anode. Electrons still flow from the anode to the cathode, but notice the reverse in the half reaction. In the battery or in the galvanic cell, copper was gaining electrons. It gained electrons until it no longer worked. In order for it to go back to the way that it started, it now has to give away all of those electrons that it had previously gained. In a galvanic cell, we use a voltmeter to measure the amount of electricity that's produced. In an electrolytic cell, we have to put in a battery or some sort of electrical energy. Also notice that in an electrochemical cell, the anode is overall negatively charged. When it becomes an electrolytic cell, the anode becomes the cathode, but it's still overall negatively charged. Think of a battery. It has a positive end and a negative end. When you take that battery and you plug it into the wall, the insides of the battery don't just reverse, and what was at the negative end goes to the positive end. It still stays the same. So the iron here was in the negative end of the galvanic cell. The iron is still in the negative end of that same battery. It's just that since we're forcing electrons to go in the opposite direction, or I'm telling that the electrons that the copper gained has to go back, or that the electrons that the iron gave away, it now has to gain it, the anode becomes the cathode. Remember from earlier, the term anode just simply means where electrons are lost, and the term cathode just simply means where electrons are gained. That's the only thing that reverses. Also note that a salt bridge can be used in an electrolytic cell. Look for the reversal of charge, as I just spoke about, that the anode is positive and the cathode is negative, where energy is supplied. Recall from the electrochemical cell lesson that we can have a spontaneous reaction that occurs, and for cell potential, a spontaneous reaction is represented by the positive cell potential. If we had to take this cell and connect it to an external electric source of voltage, it would have to be greater than 1.100 volts for the reverse reaction to take place. That is, electrons would be forced into the zinc electrode and removed from the copper electrode only when the cell potential is greater than 1.100 volts. The net reaction taking place in the electrolytic cell will be the exact opposite of the net reaction taking place in the electrochemical cell. Since it's the exact opposite, the sign will be reversed on cell potential. Remember that no matter if we have an electrochemical cell or an electrolytic cell, oxidation always occurs at the anode. This is sometimes a trick question on an exam. In an electrochemical cell, the electrons are freed at the anode, therefore the anode is the negative end. In an electrolytic cell, the electrons are withdrawn, therefore it will have a positive charge. Reduction always occurs at the cathode, regardless of if it's electrochemical or electrolytic, because the term cathode just simply means where electrons are gained. In an electrochemical cell, the electrons are removed, therefore it has a positive charge. In an electrolytic cell, they're forced into the cathode, therefore it has an overall negative charge. It is very important to keep these differences straight. There are three different types of questions we're going to look at here under electrolysis and the electrolytic cell. I will tell you that in recent years, none of these questions have been covered on the public exam. And if you're reviewing for the public exam and time is of the essence, I would strongly suggest that this be put to the bottom of the list because it's highly unlikely that you'll actually see this in your public exam. The first question looks at the electrolysis of water. Now, pure water cannot carry a current. In order to decompose water via electrolysis, some electrolyte, like potassium nitrate or sulfuric acid, must be added in low concentrations. The water that we use in our everyday life can carry a current because it's not pure water that we're using. This is the apparatus used to decompose water. In order to predict the electrolysis reaction that happens for water, we first need to write out the redox half reactions. These two redox half reactions for water at the anode and water at the cathode can be found in your cell reduction table. These half reactions will also be used in a later question. Therefore, I suggest you perhaps put a dot by these in your reduction potential table and either A, remember where they are when you go to do future questions, or memorize them all together. In order to predict the electrolysis reaction, you now have to take these two half reactions and add them together. As with any other question we've been looking at, when we add them together, the total number of electrons lost must equal the total number of electrons gained, and therefore they can cancel out. Notice we have 2 waters and 4 waters as reactants, so instead of writing that as 2H2O plus 4H2O, we'll simplify that down to 6H2O. When we add the cell potentials together, we get an overall cell potential of negative 2.06 volts. The negative cell potential shows that the reaction is non-spontaneous. This will be the same for all electrolytic cells. Overvoltage or overpotential is the voltage in excess of the theoretical value required to produce a particular electrode reaction in electrolysis. For instance, in the electrolysis of water, one would require at least 2.06 volts in order for this to occur. The second type of question is the electrolysis of molten salts. Recall from previous education that molten simply means melted form, not liquid form, but melted. It's just so warm that it has melted, kind of like molten lava. Ions of molten salts, like sodium chloride, have some freedom of movement and hence can carry an electrical current. So when sodium chloride is in solid form, it cannot carry an electric current, but when it is in molten form, it can. This would be the apparatus used for that. To predict the electrolysis reaction, you first have to write out the redox half reactions. Well, we're talking about molten sodium chloride, meaning we're talking about NaCl in liquid form. It's just simply melted. Since this is a molten salt or an ionic compound, it will exist as 2 different ions, Na positive liquid and Cl negative liquid. Once you've identified what the 2 different ions would be in liquid form, you have to find them on the reduction table. Just note that they will not be written as liquid on the reduction potentials table, they'll be written as aqueous, but we still take the half reactions from there. Next, we will want to add these 2 half reactions together. However, notice that the number of electrons lost does not equal the total number of electrons gained. Therefore, we need to multiply the cathode reaction by 2. Once the cathode half reaction has been multiplied by 2, we can now cancel out the number of electrons lost and the number of electrons gained. And we can write out the total overall reaction. However, do recall that a positive sodium ion and a negative chloride ion will be strongly attracted to one another and would prefer to be in the state NaCl liquid. Therefore, instead of writing it as 2Na positive plus 2Cl negative, we're going to write that as only 2NaCl. And that would be the complete overall reaction. The last type of question you will see is the most complicated, and that is the electrolysis of aqueous solutions. Unlike the electrolysis of molten salts, the electrolysis of aqueous solutions involve competing reactions at the cell electrodes. What this means is that an aqueous solution, by definition, means a solution that has been dissolved in water. Therefore, at each of the electrodes, there's no longer just one type of reaction happening. We have competing ones. Either A, the solution that was put into the electrode, or B, the water that was dissolved into it. So there are 2 possible oxidation half reactions and 2 possible reduction half reactions. In order to predict the products, we need to examine those 2 reactions happening at the anode and those 2 reactions happening at the cathode and determine the overall cell reaction that requires the lowest current. The rules for solving such a question are as follows. First, you need to be given the electrolyte, the one that is an aqueous solution. We write the heading Anode Possibilities. Under the anode possibilities, we will write the anion and its half reaction that was given to us, and the voltage. You'll find this from the cell potential table. And we also write out water and its half reaction and the voltage required. Recall from the first style of question, for the electrolysis of water, you were hinted at either A, remembering where this is in the reduction potentials table, or just remembering it all together. Then we write down the cathode possibilities, and we write out the cation, its half reaction, and the voltage. And we also write out the reduction half reaction for water and its voltage. Again, either remembering from the cell potentials table or memorizing it all together. Then, from each possibility, from the anode possibility, we choose the more positive voltage, and under cathode possibilities, we choose the more positive voltage, and we add those 2 together. For example, predict the half reactions and determine the actual products from the electrolysis of this example. Notice that we're working with aqueous solutions, therefore this is an aqueous question. So the first thing we need to do is write out the anode possibilities. Anode is where oxidation takes place, so we'll notice that the first half reaction is undergoing oxidation. So we'll write that down under anode possibilities and we'll carry the cell potential with it. And we also have water happening where we have either A, remembered where it's to in the cell potentials table, or memorized it all together. The next step is then to write down cathode possibilities. Cathode is where reduction takes place, so we'll carry down the copper half reaction with its potential, and we'll write out the water half reaction, where we've either A, remembered where it's to from the cell potentials table, or we've memorized it all together. Then, from each one of the possibilities, we need to choose which one is more positive. In the first one, we have negative 2.01 volts, and we have negative 1.23 volts. Which one of these is more positive? And that would be the water half reaction. So that's the one we're going to choose that happens at the anode. Then we have 0.34 volts and negative 0.83 volts. Which one of those is more positive? Well, that would be the 0.34. So the copper is the one that's happening at the cathode. So we take the water and we rewrite it. We take the copper half reaction and we rewrite it, and then we add them together. The total electrons lost equals the total number of electrons gained, so we don't need to manipulate it. We can just simply add them together. And we can take the negative 1.23 volts and the 0.34 volts, and we can add that together to get an overall cell potential of negative 0.89 volts. Since the electrolysis of aqueous solutions would not be spontaneous, it does make sense that we'll get an overall negative answer. You should take some time to go through the 3 different applications of electrolysis and take some time now to work on the worksheet.